Looking at number 4. This has an A and a B, so we're going to having to turn this page over to look at B. Bond energy is related to bond length. Okay, bond energy, bond length. Use the data table in the tables below. Use the data in the tables below to arrange the bonds listed in order of increasing bond length from shortest to largest. So bond length. Now notice that the only information that we're given here is bond energy. So we're going to have to understand the relationship between bond energy and bond length in order to answer this question. Now, what we're supposed to know about bond energy and bond length and the relationship therein is that as bond length increases, bond energy, meaning the amount of energy required to break that bond, decreases. So this is an inverse relationship. This is an inverse example of inverse proportionality. So if I'm supposed to list this in terms of bond length from shortest to longest, I need to find the largest bond energy. The largest bond energy, okay, bond energy being very big, that will make bond length very small. So that's the relationship we're looking for the largest bond energy. So this looks like this is number 1. Hydrogen chlorine is number 2. Number 3 goes to hydrogen bromine, and then 4 is hydrogen and iodine. Now we're looking for pretty much the same idea for B on the back here, but notice that we're looking at all carbon-carbon bonds. Now there's carbon-carbon single bond, carbon-carbon double bond down here, and then a carbon-carbon triple bond over here. But the idea is the same. We're given bond energy, right? Bond energy. As bond energy increases, bond length decreases. And so we're still trying to list this in terms of bond length from shortest, okay, from shortest to largest. So I want to start with the shortest bond length. Well, if I want the shortest bond length, I need the smallest bond length, I need the largest bond energy. So that would be the triple bond, followed by the double bond, and then the longest bond is going to be the single bond. Now the only thing I want to add to this is this should make sense. If this bond energy here for the carbon-carbon triple bond is the largest out of all of the carbon-carbon bonds, that should be fairly intuitive because it's triple bond. It's 3 bonds as opposed to 2 or 1. This is a stronger overall bond, so it's going to take more energy to break that, right? To break all 3 bonds. When you only have 2 bonds, meaning 4 electrons shared between the carbons, you have slightly less bond energy. Slightly less energy is required to break that carbon-carbon double bond. And then with the single bond, the least energy is required out of all 3.